Welcome back. We are doing Thermodynamics homework. This is Thermodynamics 1. The homework is homework 5, which is energy balances and first law analysis on open systems. We're doing problem number 4. Problem number 4 is out of Koretsky's textbook 2.66. So if I go to 2.66, let's see here. I have a stream of air and it's compressed in an adiabatic steady state flow process. Okay, so I got a compressor. Okay, so oh no, compressor is, comes in big, comes out small, and so there's a rotating shaft here. Okay, got stuff coming in, I got stuff coming out. What is coming in is air. N dot I equals 50 moles per second. Let's see here. Yep, so I got 50 moles per second. The inlet is at 300 K in 1 bar, so P in is equal to 1 bar. T in is equal to 300 Kelvin. What the outlet is at 10 bar, so I compress this a good amount. Okay, and a temperature 70 degrees Celsius. Okay, T equals 70 degrees Celsius. Okay, oh no, reading a wrong problem. Just coming out of 10 bar. Coming out of 10 bar. Okay. You estimate the minimum power that the compressor uses. You may assume air behaves as an ideal gas. So the minimum power would be well, I'm not sure what the minimum power would be. I have to do an analysis. It's going to be one or two cases. Either the minimum power is associated with adiabatic, or the minimum power is associated with isothermal. Because with compressors, sometimes, with things like this, sometimes you want them isothermal, sometimes you want them adiabatic. But those are kind of our two extreme cases. Let's look at kind of this either and see, like not as isothermal or as adiabatic, and see which one's kind of gonna give us the least amount of work, because, the work is coming into the system. So I definitely, so I can assume no boundary work, okay? It's not expanding, it's not contracting, it's a rigid system, okay? I'm not going to assume adiabatic yet. I'm not going to assume isothermal yet. I am going to assume an ideal gas because it's air. Let's see here. I'm also, for the sake of this problem, I shouldn't, but for the sake of this problem, I'm going to assume the heat capacity is constant, at least for now, while I figure out which one would be better. Okay, because it's not really going to change things, it's just going to make things simpler in my head. I'm going to assume it's steady state, and I'm going to assume it has no leaks. Okay, and I'm also going to assume that delta KE and delta PE are pretty much 0. Okay, so I do my mole balance, I minus summation of excess, N dot E equals dN dt. Control volume, that goes to 0 because it is steady state. There's no leaks, so the only thing that's coming in is this one, and the only thing coming out is this one. They are equal to 0, so that means what comes in is equal to what comes out. Okay, which is equal to my flow rate. Okay. There's my mole balance. Now my energy balance. Summation ends N dot I HI plus 1/2 B squiggly squared I plus GZI minus exits. N dot E HE plus 1/2 V squiggly squared E plus GZE plus Q dot plus work dot equals DU dt plus EK plus EP. Control volume, that goes to 0 because it's steady state. Okay, those go to 0 because the kinetic energy and the potential energy are pretty much 0. So I have N dot I HI minus N dot E HE plus Q dot plus work dot equals 0. Now again, I don't know if this is isothermal or not. Okay, you know, I don't know if it's isothermal or if it's adiabatic, in which case is the best. Okay, so let's make it so it's kind of work equals, because that's what I'm basically trying to find out. I'm trying to find out what's the minimum amount of work, and so I'm going to have N dot, because I can combine them, because according to my mole balance they're the same, so N dot HE minus HI minus Q dot, and then that. Okay, this is an ideal gas, and so this can become, now this would be no matter what, ideal gas, steam, whatever. Now it is an ideal gas, so this becomes Cp dt, okay, T in, T exit, okay, minus Q dot. Now, if this is an ideal gas, if this is isothermal, well, if this is isothermal, oh wait, it's not, it can't, well, yeah, if it's isothermal, then it's doing no work. So, yeah, it kind of has to be adiabatic. It doesn't make sense for it to be isothermal. If I'm doing work on the system, I have to pull out all that work from the heat, you know, to get it down to the pressure, okay, to get it to that pressure. And so, I guess technically, well, I guess that would be the best case scenario, is that I have no work. In this case, it would be no work, because that would be the smallest amount I could have, okay? Because, all the heat that goes out of the system, so this would become positive because I'm doing work on the system, so that would work out. But it wouldn't tell me anything because I don't know how much heat is coming out of the system, okay? I don't really know what the change in temperature is either, though, do I? No, I do not. So, let's see here. Maybe I'm missing a piece of information. We're doing problem number 2.66. A steam of air is compressed in an adiabatic. Oh, it says adiabatic. Ha helps to read the problem. Okay, so that's 0. Okay. So my temperature is. I must be missing something else. The inlet pressure is this. The outlet temperature pressure is that. Estimate the minimum power that the compressor uses. Well, the minimum power that it uses is 0. Because it would be 0. If it's adiabatic, it has to be 0. Because it doesn't matter what the exit pressure is. It's only a function of temperature in this case. So technically, the minimum power to do this is 0. Because it's an ideal gas. Now, is that realistic? Obviously not. So, I mean, I probably cannot assume an ideal gas in this case. And I probably shouldn't. I should probably use some other equation of state, for this. Even a van der Waals would be a better estimate than this as an ideal gas. But technically, the minimum amount of work would be 0 in this case because it's adiabatic.